Okay, welcome everyone to the EA seminar. Today we have with us Chelsea Finn. Also for the first time, note that the talk is being recorded live on YouTube. So the setting for questions, if you are on Zoom from MIT, just unmute yourself and ask the question. If someone else is also making a question, you can raise your hand within Zoom and I will call your name. And then for those of you on YouTube, you can just leave a comment and at the end of the talk, we will go through the most popular questions. Okay, so Chelsea Finn is an assistant professor in computer science and electrical engineering at Stanford University. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. She received her bachelor's degree in EECS at MIT and her PhD in computer science at Berkeley. Her research has been recognized through numerous awards, such as the ACN Doctoral Dissertation Award, a Facebook Fellowship, and the MIT Technology Review 35 Under 35 Award. And her work also has been covered by various media outlets, such as the New York Times, Wired, and Bloomberg. Throughout her career, she has sought to increase the representation of underrepresented minorities within computer science and AI by developing an AI outreach camp at Berkeley for underrepresented undergraduates across 4 universities and leading efforts within the Women in Machine Learning and the Berkeley Women in CSC communities of women researchers. I'm especially excited about having Chelsea with us today, and I'm sure other PhD students will feel the same because she set the gold standard for what an awesome PhD should look like. We're often told that graduate school is about doing one thing really well. Chelsea managed to do 3 seminal contributions and many others in reinforcement learning for robotics, visuals foresight, and of course, meta learning and fusion learning. Welcome to our seminar.
Thank you for the introduction, Farron. So today I'll be talking about how we can move beyond the training distribution, and feel free to ask questions throughout, like Farron mentioned. So Farron already said this in the introduction, but I'm interested in how we can develop broadly intelligent behavior through learning and interaction. And to study this problem, we like to actually study robots in the real world, robots that can learn motor skills like the kinds of things shown here, and be able to apply those motor skills in a wide range of situations. The reason why I like to study robots in the real world is that I think they can teach us things about artificial intelligence. General purpose robots must be able to generalize across tasks, objects, terrains, and so forth. And I think that they provide a really nice platform to study some of the most challenging problems in artificial intelligence. And today I'd like to talk about generalization and provide a perspective on how we can broaden the generalization of artificial intelligence systems, robots, but also others outside of robotics as well. When thinking about generalization, I think we often find ourselves in a situation that looks like this, where the data distribution at test time that we'd like to be able to handle is much broader than the distribution of data that we see at training time. For example, the training data distribution may be data collected by a robot in one of our lab environments, and the desired test distribution might be in the real world, where the robot must be able to manipulate many different kinds of spatulas, many different kinds of objects, and do so in a variety of different environments. So we need to think about how to tackle this sort of problem. I think that one natural reaction to tackling this problem is thinking about, well, I know how to generalize to many different kinds of spatulas. I know how to generalize very broadly. Can I build in my knowledge into the algorithm in order to help it generalize more broadly as well? For example, we may think, okay, well, we know things about physics. Can we build a physics simulator and use data from that physics engine in order to help the robot to generalize? Or can we build in some notion of objects into the algorithm? Or we know about certain kinds of equivariances that exist in the world. Can we build in those kinds of things? Or build specialized architectures that might be able to build in some of this knowledge? While this is a very natural reaction, I think that there's a couple issues with it. The first is that while we humans are very good at generalizing, we don't actually know how we generalize. There's a whole field devoted to this in neuroscience and cognitive science, into studying how humans develop the kinds of behaviors that we do. And even if we did know how to generalize, even if we were very confident about the way that we're actually solving these problems, we also don't know how to program it into our artificial intelligence systems. In many ways, this is kind of the approach underlying symbolic AI. And so what I'd like to talk about today is if we can do something better. I think it's not necessarily a great idea to rely on neuroscience and cognitive science, an entire field of science, in order to build, in order to try to solve our field, artificial intelligence. But even if you do think that this is a good approach to AI, I think that some of the ideas that I'll be talking about today will also be helpful for broadening generalization. Okay, so when faced with this kind of problem, there are two approaches that I'd like to propose as alternatives. The first is, if you want your agent to generalize broadly, instead of altering the algorithm or the model to generalize further, can you figure out how to train it on equally broad data? Can you figure out how to broaden your training distribution and push it out to look more like your desired test distribution? To do this, we may actually need to develop new algorithms that can learn from scalable data sources rather than using algorithms that rely on very specific data sources. For example, online reinforcement learning requires very specific data from a certain policy. And second, beyond building broader data sets, can we figure out what assumptions will allow the algorithm to generalize further? And in particular, what I mean by this is that in machine learning, we typically assume that we have this IID assumption, independently and identically distributed data. While this is a very convenient assumption, it's also a very weak assumption. And I think that there may be other assumptions that we can build into our algorithms so that they can generalize more broadly, without having to necessarily build in knowledge ourselves. Okay, so I'm going to briefly touch on the first point, because I think that's a really important point, but then the rest of the talk I'll focus primarily on the second point. Okay, so if we want to think about training on broad data sources, we first need to look at what our data looks like in robot learning. And if we first look at a few years ago, and even before that as well, some of the videos that I showed at the beginning, for example, we saw data that looked like a single object trying to perform a single task in a single environment. More recently, we've seen algorithms that can learn from many different objects, but still a single task, like grasping, for example, in a single environment. And then even more recently, we've seen more progress trying to collect data sets with many different objects, many different tasks, but still a single robot in a single environment. And if we contrast, it seems like we've been making progress kind of in the breadth of the data we can train our algorithms on. But if we contrast this with what data in machine learning looks like, it looks something like ImageNet. And this is, of course, 10 plus years ago. And really, they aren't even comparable. ImageNet has many different objects, tasks, environments, viewpoints, lighting, and so forth. And by training on such broad data, ImageNet models generalize very broadly, and they transfer also to many different kinds of tasks. I think essentially we've seen time and time again that data scalability within deep learning has a much more substantial effect on generalization than changes to the algorithm. And we've seen this with ImageNet, with things like GPT-3, as well as other stories in settings like speech recognition. So I think that instead of building necessarily better algorithms, we need to think pretty critically about this sort of scalability. And to accomplish this, I think there are essentially two things we need to do. I think we need to leverage large and diverse data sets in the context of embodied learning, and also build algorithms that can learn from these large and diverse data sets. And so some work that we've been doing on the first angle is we've been looking at how we can share data across institutions. Of course, sharing data across institutions is done all the time in machine learning. In robotics, this introduces new challenges because we need to be able to generalize to new robots and to new lab environments. We've been collecting data that looks like this and seeing if we can apply some of our existing algorithms to this kind of very challenging and diverse data. And we've also been looking at if we can leverage videos of humans, a very broad source of data that's available on the internet. And if we can start to learn from videos of humans, for example, some of the videos shown here on the left, then we may be able to start to tap in to this extremely broad data set on the internet. So this is kind of the first angle. How can we start to leverage these kinds of diverse and large, broad data sources? But also if we can build algorithms that can learn from them. And I think that many of the classic online reinforcement learning algorithms and imitation learning algorithms aren't necessarily well suited for these kinds of data sets. And a number of students in my group have been looking at batch offline reinforcement learning algorithms that can in principle, hopefully at some point scale to these very broad data sets, both model-based algorithms as well as model-free algorithms for doing this. And we've also been looking at if we can build offline meta reinforcement learning algorithms that can leverage static data sets across multiple tasks in a way that allows us to learn a new task more quickly, so that hopefully we can leverage these very large and diverse data sets, which will be by nature static. We can't be kind of continuously, they may be continuously added to, but we need to be able to learn from kind of previously collected data in order to be able to scale. Okay, so that's kind of a very kind of brief overview of why I think data scalability is really, really important and some of the work that we've been doing along that direction. But I'd like to probably focus the most on trying to figure out how we can generalize even further. And I'd like to focus on this, and I think this is really important because it gets at maybe some of the more, some of the challenges that will come up when we actually start to scale, and really starts to hit some of the more fundamental assumptions of, and more fundamental challenges with kind of standard machine learning. Okay, and to start to think about what sort of assumptions we should build in, I'd like to look at, kind of think about things from the standpoint of reinforcement learning in open world environments. Essentially a setting where a robot is in a very huge world and it's going to need to be able to generalize to beyond its training distribution because each new state that it encounters in that world will not necessarily look like the states that it saw previously. And specifically, we'll look at 3 different aspects of this problem. The first is being able to handle persistent continuous shifts throughout the learning process, such as variation in the lighting over night and day, variation in wind, variation in user preferences or mood over the course of a day as well. We'll then look at sharp changes in new situations that are caused by more major events, such as having new demands from a customer or a user, or entering a new building in the world. And then lastly, we'll talk about kind of more generally trying to accelerate future learning by leveraging previous experience in these kinds of open world environments. Okay, and to study these sort of settings, we are going to need to introduce additional assumptions. This, I think, is inevitable in order to go beyond the training distribution. And the goal will be to make these assumptions mild, yet also powerful in what they allow us to do. Okay, so let's first talk about persistent continuous shifts. Whenever trying to look at a new problem, it's worth considering what prior work exists. And one notable prior work in this area is the notion of partially observed Markov decision processes, where you have some sort of partial observability in the world that may be shifting throughout your lifetime. And this is a problem setting that does, in fact, cover persistent and continuous shifts. But one of the challenges with this setting is that it's perhaps too general and it's difficult to develop algorithms that solve such a general problem. Now, there's also some prior works such as Bayes adaptive MDPs and hidden parameter MDPs that can also model kind of partial observability. And in particular, what these algorithms do is they assume that there are some hidden parameters underlying the transitions and the rewards, but they assume that these hidden parameters are stationary. Essentially, they're drawn from a single distribution at the beginning of each episode, held fixed, and at the next episode, they're drawn IID from that same distribution as the previous episode. So motivated by perhaps kind of these 2 problem settings, we wanted to be able to capture a setting that wasn't quite as general as POMDPs, but can also model this sort of persistent and continuous shift. So to do so, we introduced what we're going to call dynamic parameter MDPs. And like BAMDPs and HIP MDPs, these will have hidden parameters underlying the transitions and the rewards, and these will be fixed within an episode. But across episodes, the parameters will systematically shift. So essentially, the distribution of the parameters for one episode is going to be dependent on the previous episode. And again, these parameters are not going to be given or provided to the agent. Now, it's natural to ask, well, how well do existing algorithms perform with these shifts already in this sort of problem setting? So let's just start with two very simple settings. One is a reaching setting where a robot manipulator wants to reach towards a goal. And the goal is going to be shifting across episodes. And also this really simple half cheetah agent that wants to run where the goal velocity is shifting over the course of its lifetime, as well as there's varying wind over the course of its lifetime. And what we see is if we apply existing algorithms such as SAC and PPO, existing off-policy, non-policy algorithms, as well as SLAC, which is something that could model partial observability, but not necessarily kind of non-stationary partial observability, we see that all three of these algorithms perform quite poorly when things are changing across the lifetime of the agent. In comparison, an oracle that can receive the kind of oracle information about what's shifting can perform very well in comparison. So we'd like to figure out how to bridge this gap and build an algorithm that can perform more closely to the oracle without requiring oracle knowledge, of course. So to do so, we're going to build upon the framework of framing reinforcement learning as probabilistic inference in graphical models. And we'll formulate a graphical model with a dynamic latent parameter that looks like this, where there's essentially now a latent parameter z that shifts, and the dynamic latent parameter is fixed within an episode, and it shifts across episodes according to some distribution that is going to underlie this edge from z to z prime. And what we can do is under this graphical model, we can formulate an objective. And one key assumption underlying the algorithm that we'll try to solve this is that we can actually predict z prime from z. And this assumption of predictability is what's going to allow us to learn under this non-stationarity. So when we formulate this objective, we get something that looks like this. This may look a bit complicated, but essentially we're, on the left-hand side, we're maximizing the probability of our trajectories and maximizing probability of optimality with respect to our policy. And what this objective looks like, what this lower bound looks like, is on the likelihood is that the first term is modeling the dynamics of the reward. So this is quite simple. And this is used to form a representation of the observations. The second term is going to be modeling latent variable shifts. So it's essentially going to be trying to form a model of zi prime given zi prime minus 1. Then we'll use this prior in this model of shifts at test time when trying to predict what will happen next. And then this last term just corresponds to entropy regularized reinforcement learning. So this corresponds essentially to a model-free algorithm that also has this model-based component that's using prediction of dynamics and reward to form a state representation, as well as this model of the shifts in order to predict what will happen next and pass this latent variable and this prediction of the latent variable into our policy. Okay, so we refer to this algorithm as lifelong latent actor critic in the sense that there's a latent variable that's shifting across, whose value is shifting across the lifetime of the agent. And if we look back at the two simple settings that I mentioned before, we see that this algorithm is able to do significantly better than algorithms that don't account for this sort of non-stationarity and start to approach the level of performance that Oracle reaches. Further, we can look at more complicated settings, such as this Minotaur robot with a continuously varying mass, as well as this, this simple 2D kind of 2D navigation setting where the agent needs to navigate as well as collect the blue objects in the environment. And what makes this setting a little bit more challenging is that there's no resets in the entire agent, in the entire lifetime of the agent. The agent is simply wandering around this world and continuously learning and also eventually learning to perform the task. And we see again in both these settings, by essentially trying to predict what will happen and predict this sort of non-stationarity into the future, it can perform substantially better than algorithms that ignore this kind of non-stationarity that may exist in the world. Okay, so essentially the takeaway is that by modeling and anticipating change, we can learn amidst non-stationarity in the world. Okay, so now that we've talked about handling persistent and continuous shifts, I'd like to talk about more sharp changes in the world and being able to handle new situations. And if you have any questions about the first setting, feel free to speak up now. Okay, sounds good. So in this setting, we're going to look at a problem setting that looks like this, where we have one training environment, one training MDP, mtrain, and we want to be able to essentially extrapolate to new test environments, mtest. And we'll start with a setting that is a simulated setting that's fairly simple. And then after this, I'll talk about a setting with a real robot. So first, we'll look at a simple simulated setting where we have this walker agent whose goal is to walk forward. The training environment is very similar to the standard like gym training environment using the Majoko physics engine. And the test environments will look like this, where this task is the same, but there may be an obstacle or force perturbation or some disabled joints that the robot encounters. Now, how might we try to approach this sort of problem? One very natural approach is robust control, where essentially you have some sort of adversarial perturbations to the agent. And this sort of approach is actually quite powerful, and it can generate a variety of perturbed situations during training such that you can actually generalize to those perturbed situations. But it has a number of downsides. First, it may sacrifice overall performance by actually trying to train for this sort of robustness. Second, it requires an adversarial optimization to actually optimize for these perturbations, which may be tricky in practice. And lastly, it may not be feasible to generate lots of different kinds of perturbations in the real world. So we'd like to take a bit of a different approach that tries to address some of these shortcomings. And in particular, our hypothesis is that policy learning algorithms and reinforcement learning algorithms in particular are brittle because they learn just one approach and one solution to the problem. And if instead we try to learn and remember multiple solutions to mtrain, then we may be able to generalize by essentially adapting that solution set to mtest. And more specifically, here's maybe kind of an illustrative example to show this. So say our goal is to reach this red circle right here. If we learn multiple solutions as shown in kind of orange, green, and blue here, then if at test time we're presented with an environment with an obstacle, some of the solutions may no longer work, including kind of the most direct solution to the goal, the green path. But if we do learn and remember multiple of these solutions, then in this situation, we can actually generalize by adapting the solution set to the blue solution or to the orange solution. Okay, so this makes a couple of assumptions in order to be able to generalize. The first is that we can adapt with a modest amount of data. This is important so that we can adapt our solution set at test time. And the second assumption is that the changes to the environment are somehow local. And more formally, what we mean by this is that at test time, the optimal policy to mtest also does well in mtrain. And under these assumptions, we can essentially expect this kind of approach to be able to extrapolate to environments mtest. And this, for example, we may be able to achieve things like few-shot robustness to local changes in obstacles, terrains, friction, and so forth. So now how do we actually develop an algorithm that learns multiple solutions? What we do is we try to learn a controllable space of diverse policies that achieve a return that's within epsilon of optimal. By controllable, I mean that we're going to try to use latent variables to learn a latent condition policy, shown here. And then we'll try to form a constrained optimization to find a controllable space of policies that all do fairly well in the training environment. More concretely, we'll optimize an objective that looks like this. Essentially, this first term in the objective is going to follow actually prior work called diversity is all you need, or DIAN. This is maximizing, you can kind of break down this mutual information term into a maximization of the state entropy minus the state entropy given Z. So this will essentially try to learn a set of policies that maximize state entropy, but in a way that is essentially predictable from Z, corresponding exactly to the kind of the first part, and the second part corresponds to the constrained optimization, such that each of these policies actually achieve a good return in the environment. Okay, and then at test time, what we essentially do is we roll out k different policies, each with different Z's, and then we return the policy and the corresponding latent for the latent variable policy that performs the best. So this is how we'll adapt our solution set at test time to the test MDP. We refer to this as structured maximum entropy reinforcement learning, or SMERL, which will be important when we look at the solutions because it'll be labeled according to that acronym. Okay, so we tested robustness to varying obstacles in the environment, varying force perturbations, and motor failures, as I mentioned before. And we're going to compare SMERL to standard SAC, which performs entropy regularized reinforcement learning. So it is maximizing entropy, but not in a way that is controllable at test time. We'll also compare to Diane, which maximizes diversity, but doesn't actually maximize return. And lastly, we'll compare to robust adversarial reinforcement learning, which corresponds roughly to the sort of robust control that I mentioned at the beginning. And when measuring 5-shot generalization and looking at kind of as the environment changes more and more from the training environment, we see that in general, SMERL is able to achieve greater robustness to different situations. So in particular, in the half cheetah obstacle and half cheetah force situation, we see that in general, it's more robust as you kind of add more and more height to the obstacle or more force magnitude. And then also in the Walker situation, we find that the situation is a bit more difficult, but we're able to either achieve similar robustness or greater robustness to these kinds of perturbations at test time. Okay, so this is one way to try to extrapolate to new environments. What about in, actually, here's some qualitative results to kind of qualitatively understand what happens. So in this case, in the half cheetah case, the goal is to go to this blue sphere. And these are the SAC policies at training time. And when we introduce an obstacle, the best SAC policy at test time looks something like this. So by not actually being able to control the way that control different solutions, it isn't able to reach the goal. While in comparison, SMERL learns kind of more diverse policies, some of which hop on the back foot, some of which stay low, some of which hop on the front foot, and even one solution that decides to backflip in order to get to the goal. And what we find is that the best SMERL policy, which is actually the one that backflips, is able to figure out how to get over this obstacle at test time, even though it was never trained with an obstacle at training time. Okay.
I have a question. How important is it that at training time, the set of solutions that work at training time is somehow like connected? So for example, in your first example that you could go kind of a bit left, a bit right, and center, would it be a problem if you could not go center and there were kind of two clusters of policies that worked well?
So you're asking in what sort of situations would you expect this to generalize?
So I'm asking the distribution of policies that can solve the training task. Do we need that set to be connected to be kind of one cluster, one spread, instead of kind of multiple clusters where you would need to control each of them?
Yeah, so you don't actually need the kind of the set of policies to be smooth in a sense. In this case, we actually used a discrete latent variable because we found the optimization to be a bit easier. You could use both continuous and discrete. And in this setting, you actually notice that one of the kind of latent variables leads to a very different policy than the other four. So I think that essentially they don't necessarily need to be a connected or smooth set of solutions.
Good, thanks.
Okay, so what about in the real world? We're gonna look at the same sort of setup where we have one training environment and a new test environment. And now we'll look at a grasping situation where we have a real robot. In this case, it was trained with the QT-opt algorithm, which is a powerful reinforcement learning algorithm that can achieve good grasping performance on a wide range of objects. And look at a variety of different test environments that include drastically different lighting conditions, transparent bottles placed in the bin that it has to grasp, a checkerboard background that's very different from what it saw during training, as well as a completely different morphology of the robot, where the gripper is translated 10 centimeters to the left of the robot. So these are essentially as drastic of changes we could think of. And if you take the original policy that had an 86% success rate in the training environment and then deployed it in these test environments, performance drops substantially to 32%, 49%, 50%, and 43%. So clearly learning kind of a single policy and then hoping for it to generalize to all these sorts of situations isn't realistic. Now, the key assumption that we're going to make, similar to the previous work, is the ability to adapt with a modest amount of data. In this case, we're not going to change we're not going to assume that these changes are local. We're really just going to kind of look at these sorts of, these are kind of examples of the settings we look at. We'll only make the assumption that we can adapt with a modest amount of data. And the simple idea that we really want to kind of start with the most simple thing, which is maybe we can just fine tune. Fine tuning has been very successful in computer vision, in natural language processing, but we haven't really validated or seen successful fine tuning in robotic reinforcement learning. And this is actually arguably a very natural place to deploy fine tuning, as reinforcement learning algorithms are designed to be able to continue to improve with experience. So what we do is very simple. The initial policy was trained on 608,000 grasps with the QT-opt algorithm. This achieved 86%. Then in the new environment, for example, in the setting where the gripper is translated by 10 centimeters, we collected only around 800 grasps in this data. So this is about 1% of the initial data set size. And this takes about an afternoon to collect. Then we took the Q function initialized from the QT-opt policy and then ran gradient descent from that initialization on the target data. And then the adapted Q function was able to achieve a much higher success by actually fine-tuning and adapting it to this new setting. And what we found is on a variety of new kind of tasks and environments with different visual and physical changes to the robot was able to see strong improvements even after just 25 new grasps. And after 400 to 800 grasps, it was able to realize performance that was almost similar to the original policy in the original environment. We also found that ImageNet pre-training performs quite poorly in this setting as well. Okay, and then here's also some video results. We'll see if Zoom allows us to play this well. Yeah, so with the harsh lighting conditions, we found that the pre-trained policy tended to try to grasp its own reflection in the bin, while the fine-tuned policy is able to do much better. With transparent bottles, we found that the pre-trained policy would try to grasp at adjacent bottles or kind of jam its gripper on the bottle, while the fine-tuned policy is able to grasp more successfully. Here's some videos of the offset gripper. Understandably, the original policy had fairly bad aim when the gripper was offset by 10 centimeters, but the fine-tuned policy really didn't have any problem handling this. And then finally, the checkerboard policy had a tendency to grasp at the boxes in the background, while the fine-tuned policy was able to figure out that those were not useful for actually getting successful grasp. Okay, so kind of the takeaway from this work, at least for me, was that you can extrapolate to pretty drastically new environments with only an afternoon's worth of data by essentially continuing to learn. And the work before that showed that we could extrapolate with even less data by making a further assumption about the kinds of changes that you'll see. And then lastly, in some of our other recent work, we've shown that with meta learning, we can accelerate the adaptation process by training for fast fine-tuning and also adapt to distribution shift with only unlabeled data from the test environment. Great. So that was a good stopping point if there are any more questions.
I just had a quick one. Oh.
Yeah, go ahead.
So I know at the beginning we were a little bit quick to dismiss kind of adversarial methods, but the setting is pretty similar to domain adaptation in computer vision, where in domain adaptation you're trying to adapt from a source distribution to a target one. Here you're trying to adapt from a train environment to a slightly different test environment. Do you think that there's any crossover that can happen between those two fields, or do you think adversarial methods just aren't fit for this challenge?
Yeah, absolutely. I think that in many ways, adversarial methods could be quite complementary to some of the things that I discussed as well, and be used to essentially augment your data distribution. One thing about domain adaptation in particular is that you usually assume that you have data of your test environment available during training. And I think that that assumption is a bit unrealistic in many practical settings. I don't know exactly what environment my robot's going to find itself in like a week from now. But I do think that some of the ideas in adversarial RL can be useful, but hopefully some of the ideas that I presented are also kind of complementary to some of those ideas, and also and kind of also can further augment the robustness of these kinds of approaches.
Awesome, thank you.
Okay, so I'd like to end on some work that's actually perhaps a little bit more preliminary than some of the things that I talked about, but also something that's hopefully more likely to bring up some interesting discussion. And this is along the lines of meta learning and accelerating future learning. And in particular, I'd like to bring up this picture again that we talked about at the very beginning, where our desired test distribution may be broader than what we train on. And we talked about how we may consider trying to build in structure to solve this problem. Now, one very classic example that everyone brings up as a really successful example of building in structure is convolutions. And this builds in the structure of translational equivariance, which exists for many sequence data, a lot of image data, and so forth. And so we'd like to ask the question, is it possible to learn this structure? And in particular, in the case of convolutions, is it possible to discover things like convolutions? Is it possible to discover equivariant and invariant structures via meta-learning? And if we could do so, maybe if we can discover things like convolutions, maybe we could also discover structures that we aren't good at building in, or that we don't know necessarily exist in the world. Symmetries, essentially. Now, you might ask, well, it seems like meta-learning is already recovering structure. Does MAML already recover things like equivariant structure and invariant structure? And for those not familiar, kind of essentially the idea behind MAML is that you're going to try to learn a set of initial parameters denoted by this network on the left, such that one gradient step or a few gradient steps leads to a network that can generalize to new examples, even when those gradient steps are only performed on a very small amount of data. Now, getting back to the question, MAML can learn equivariant initial features. They could learn features that capture certain equivariance or invariance properties, but these properties may not actually be preserved in the gradient update. So while some initialization that it learns may be equivariant, the post-update function may not share that equivariance, especially if you kind of give it some arbitrary data that's maybe a bit different than what it saw during meta-training. And so the goal of this work is going to try to figure out if we can decompose the weights of the neural network into equivariant structure and the corresponding parameters. For example, in convolutions, can we decompose, if we wanted to discover convolutions, can we decompose the weights into the weight sharing strategy underlying convolutions and the parameters of the corresponding weights, of the corresponding filters? And if we could do this, then we could update only the parameters, only like the filter parameters in the inner loop, and retain the equivariance throughout the inner loop update. And this would allow us to essentially learn equivariances that are true across a range of tasks and keep those equivariances fixed in the inner loop of the algorithm. So if that isn't clear, hopefully it'll become a bit more clear in the next couple slides. And to think about this question, we wanted to think about, well, first, how are equivariances actually represented in neural networks? And first, let's look at an example. So we can look at the example of convolutions. And a 1D convolution looks like this, where you have some set of weights, some set of parameters, W, that correspond to the filter. And that filter is slid across the image, such that when it's at the first position, it outputs Y1. When it's at the second position, it outputs Y2. And when it's at the third position, it outputs Y3. Now, this is one way to represent a convolution. But another way to represent a convolution is actually with a fully connected layer, a layer that looks like this, where essentially those filter parameters are copied in the weight matrix multiple times, and the rest of the weight matrix is just 0. So this is one way that we can essentially represent equivariances as equivariance like convolution as a fully connected layer. A way that we can essentially encode this sort of translational equivariance in a fully connected layer. And there are also other sorts of things that you can represent in a fully connected layer as well. This is just one example. Now, what we're going to try to do is essentially try to reparameterize this weight matrix into the weight sharing pattern and those parameters A, B, C. And so the way that we're going to do this is we're going to try to take some vector of parameters. This will correspond essentially to like ABC on the previous slide. In this case, there are just two parameters, yellow and green. And then we're going to multiply that by what we'll call this sharing matrix. And this sharing matrix will encode how those parameters are copied, how those parameters are copied into your larger weight matrix, such that you actually have a weight matrix with these shared parameters. So the result of this sharing matrix times parameter is a vector of weights, and then we'll reshape this vector of weights into a matrix of weights. In this example, we get this 2x2 weight matrix of weights out. And this actually example corresponds to permutation equivariance, where if you hit this weight matrix on the right with an input, any input that you give it, it's a function that kind of exhibits this sort of permutation equivariance. So if you permute the inputs, the outputs of this function will also be permuted. Okay, so essentially with this kind of reparameterization of a weight matrix on the right into the sharing matrix and a set of parameters on the left, you can actually theoretically prove that this directly can represent a decoupled equivariant weight sharing pattern along with filter parameters. And you can prove this for all group convolutions for finite groups G. And finite groups G includes translations, rotations, reflections, and a variety of other equivariances. Okay, so now that we have this reparameterization of a weight matrix into the sharing matrix and the parameters, the sharing matrix U and the parameters V, what we can do is we can essentially meta-learn the equivariance. So what we can do is in the inner loop, we'll only update the parameters V. So this will correspond to this first row is showing the neural network. You take the inner loss update. This is passed through U into V. So you only update V, and then after the gradient update in the second line, you have V prime, and the weight sharing matrix U will be fixed. Essentially, the equivariance will be fixed. And then in the outer loop, you're going to learn both the equivariance matrix U, the weight sharing matrix U, as well as the initial parameters V. Okay, any questions on how this works before I go to some of the results? Okay, so to recap again, we essentially have our weight matrix is decomposed into a sharing matrix and a set of shared parameters. And then in the inner loop, we only update the shared parameters and we keep that weight sharing matrix the same. Okay, so we refer to this as meta-learning symmetries by reparameterization, or MSR. And in our experiments, we wanted to answer 3 questions. The first question we had is, can we discover convolutions from translationally equivariant data? So to do this, we constructed a bunch of tasks, actually just with synthetic data, where we constructed a bunch of like ND functions that were just a vector and that were translationally equivariant. And each function, all functions were translationally equivariant, but they were different functions for different tasks. And what we found is that if we compare MSR, starting with the fully connected layer, is able to achieve performance that's comparable to MAML with a convolution layer. And both of these were able to outperform MAML with a fully connected layer or a locally connected layer, which isn't able to essentially encode those equivariances, that translationally equivariant nature of the tasks. And further, if we actually inspect the weight matrices that MSR learns, it looks exactly like the convolution matrix that I showed earlier. So essentially, it's able to learn the structure of this 1D convolution from translationally equivariant data. Now, the second question we had is, can we actually discover something better than convolutions? And so first we looked at data with partial translation symmetry. So this essentially corresponded to a locally connected layer with 1, 2, or 5 shared filters one shared filter with a locally connected layer corresponds directly to convolutions, while 2 corresponds to something that's a bit more, that only has partial translation symmetry, because you have different filters for two different filters. Some filters are applied at some parts of the input, some filters are applied at the other part of the input. And what we found is with these, as you kind of move to 2 or 5, which only has partial translation symmetry, MSRFC was able to outperform convolutions because it's able to better capture the symmetry that existed in the data. And of course, both of these are able to outperform fully connected layers and locally connected layers, which aren't able to leverage any of the symmetry structure. And we also looked at data with translation, rotation, and reflection symmetry. And we found that MSR, actually starting with a convolution layer in this case, was able to recover the additional rotation and reflection symmetry and do better than MAML with convolutions, which isn't able to capture these kinds of symmetries. Okay, and then lastly, we looked at if we can learn symmetries from augmented data. And to do this, we had a simple algorithm where we essentially took a task data split into train and val. We augmented only the val data, and in the meta learning loop, had the inner loop correspond to normal data and the outer loop corresponding to augmented data. And essentially what this is trying to do is to bake data augmentation into the architecture or into the update rule, such that when you then apply this kind of learned update rule or learned architecture to a new task, it sort of gets that data augmentation already for free, even if you trade on unaugmented data. And what we found is that MSR is able to essentially bake this sort of data augmentation into the architecture. So we tested this on OmniGlot and Mini-ImageNet with data augmentation such as reflection, rotation, random crops, and so forth. And MSR was able to better capture this data and better perform on unaugmented data at test time compared to MAML, almost no inner loop, and protonets with the same sort of augmentation meta training. Okay, so essentially MSR provides a framework for understanding the interplay of features and structure in meta learning, which I found quite interesting throughout the course of this project. And some speculation, I think that kind of this work in many ways is very preliminary and very early in its lifetime. But I think that if we have the ability to recover things like convolutions, perhaps there are other equally powerful equivariances that we can also learn from data. Okay, so to wrap up, I talked about at the beginning, if you want your agent to generalize broadly, try to broaden the training distribution by leveraging large data sets and building algorithms that can learn from them. Then I talked about how we can maybe figure out some assumptions that allow our algorithm to generalize further. And these assumptions may include things like predictability, local changes in the environment, a modest amount of test data, and some amount of shared equivariant structure. And by making these assumptions, we can learn amidst non-stationarity, extrapolate to new situations, and achieve few-shot generalization, including to settings where you need to extrapolate to data that looks different from what the inner loop is giving you. Of course, these aren't the kind of final answers on things, but I think that this general recipe of broadening the data and figuring out better assumptions for further generalization will allow us to get pretty far. And I'd love to hear other ideas on other assumptions that we may be able to introduce to be able to generalize better. Okay, I'd like to thank my students. If you're interested in learning more, I developed a new course on multitask learning and meta learning, and all the lecture videos are available online. And I'd be happy to take some questions. Thank you.
Thanks, Chelsea, for a great talk. Are there any questions? Evan, I believe you also had a question from before.
Yeah, this is a very, very quick one. Just in not the last set of results that you showed, but the one right before that, what was the evaluation metric used there? The one where lower was better?
Oh, mean squared error.
Ah, okay.
This one? Yeah, all of this is mean squared error, sorry. Yeah.
That makes
so
more
lower
sense.
is better. Looks like Lucas has a question.
Yeah, thanks for the talk. I guess one question I had is like going back to the old papers, like the 2015, 16, you're doing things like peg and hole and like the scooping, which are like pretty hard tasks. And then I think, you know, as the work's gone on, we've gone to like definitely broader, you know, sets, harder generalization, but sort of we're kind of like in like pushing and grasping tasks. So do you see those like coming together or sort of what's the future there?
Yeah, absolutely. I think that there are these two axes of sorts. One is complexity of the task and maybe like time horizon and so forth, and the other is generalization. Recently, my lab has been focusing a lot on the generalization angle and sacrificing complexity, understandably in many ways. I think that it's still really important to keep in mind complexity and not only be able to develop algorithms that can do very simple things. And I think that we will be able to bring things together together at some point. I think that perhaps the important thing to be thinking about along these lines is exactly like once we actually start building algorithms that are leveraging much larger data sets than what we're already doing, how does that change our algorithms? Because if we're starting to be this kind of, some of these things may change our algorithms pretty drastically. Maybe we won't be doing online reinforcement learning. We'll be learning from the kind of large offline data sets, and that may also think about how we learn more complex tasks as well. One kind of more specific answer to this question is that we have been looking at leveraging videos of humans, specifically for tasks that require using an object as a tool. And I think that videos of humans are one source of data that you can acquire at scale, but also acquire interesting and complex behaviors. And I hope that perhaps with a data source like that, we may be able to really hit both on the complexity angle as well as on generalization.
Yeah, I think that makes a lot of sense. I think one of the hard things is like when you're doing random policy, unless you have a pretty simple task, it's hard to get anything meaningful, at least at the beginning. So, all right, thanks a lot.
I completely agree. Yeah.
Brian, you had a question?
I have a question.
You go ahead, I guess.
So, hey, Chelsea, I was thinking about the non-stationarity environment stuff a little bit, so the middle part. And I was wondering, in non-episodic domains, I mean, I didn't get to stare at the objective functions and stuff long enough, but would that same approach probably work okay if you just had a robot that was living one long life and the latent variable is moving according to some Markov process or something, it's just not observable?
Yeah, so in this last experiment, this is a really simple 2D world where the agent is collecting different,
I missed
objects.
that. Okay, yeah.
This is actually not episodic and like just a single long life. The more complex environments, we had trouble doing this sort of thing because if you have this legged robot, it could flip over and be irreversible. But you could absolutely apply this sort of algorithm to a single long life.
I see. Yeah, because I mean, one interesting use case of this, which came up for me a long, long time ago, was if you have two agents doing like cooperative reinforcement learning, then from my myopic perspective, if I'm one of the agents, what you're doing looks like non-stationarity in my world.
Yeah.
And if I can be robust to that, then I can actually make the two agent learning case more stable. So that, I mean, you probably have a much better method of doing that. It would be interesting to see if that would help for two agents.
Yeah, the first author of this, Annie Jia, she's actually working on the two agent problem right now in collaboration with me and Dorsa.
Okay.
So yeah, it's a great idea.
There is a question on YouTube where Sandipan Haldar asks, do you expect SMER to generalize across varying environments setting like the ProcGen benchmark or the CoinRun environments?
Yeah, that's a good question. I'm not familiar with all of the details of those environments. I think that one thing that we were looking at in this setting was that we didn't really change the state space of the robot. The state space was still the kind of joint angles and joint positions of the robot. And I think that if the state space and the observation space is changing drastically, then generalization may be potentially more difficult. I think that ideas along those lines could be used in that sort of setting. We personally haven't actually experimented in those kinds of settings where the observations are changing drastically.
Evan, you had another question?
Yeah, I just put this in the chat. In the changing environments problem, the idea of learning multiple different policies in the train environment, and then one of them might be generalized as well to the test environment is certainly appealing. But it seems restrictive that, like, especially if we wanted to generalize this to robotics, that we need a single agent to be able to learn these policies. Has there been work done into the sharing of policies between multiple agents, possibly in different environments?
Yeah, I'm not an expert on multi-agent RL by any means. I feel like I have seen work on sharing policies between multiple agents. I think that in general, my perspective is that this is essentially like the question of whether you use weight sharing or not. And it seems like that mostly should be a question of whether it helps the optimization. I think that in general, this approach doesn't need to use weight sharing at all. You could apply the same sort of algorithm to, instead of learning kind of a latent condition policy, you could learn just 10 policies that are completely separate and have no shared weights. So I think that the question of whether you share weights or not is somewhat independent of the objective in the algorithm.
All right, thanks.
Cool. So it's 3 p.m. So let's leave it here. Thanks, Chelsea, for a great talk.
Thank you, everyone.
Bye.